Taking a look at the optical portion of our project, we were able to demonstrate the collimation of the beam emitting from our laser diode. Here we are using our laser diode with an objective lens from the lab that has the same specifications as the lenses we purchased. The laser was operating at a current of 40 milliamps, and as it can be seen, we get a nice beam spot of about 1 centimeter in diameter at a distance of about 3 feet to where the wall was.
At defining the power ranges and collimating beam, we see if the phototransistor can detect when there is a hit in ambient light, a hit in dark light, and to see what kind of power it reads when it gets hit in ambient light at the maximum of 32 milliamps. Then we do the same for the misses on the phototransistor at with ambient light and no light, and find its power too at the minimum of 29 milliamps.
In this, we are measuring the output power of our laser diode along the higher end of the operating current, ranging from 33 milliamps to 40 milliamps. The audio from this video is muted, but I am calling out the current in steps of 1 milliamp. We wanted to gather this data since this is the first time we've been able to use the laser diode we purchased for our project, and we are still tuning some of the settings in the code pertaining to the phototransistor and the identification/hit messages.
So now onto the software side of things. This is the actual code behind the entire photo tank controller that we'll be using to communicate with our photo tank. Let me go ahead and open it up. As you can see here, typically what happens on startup, which I don't have the GStreamer pipeline ready, is the stream will actually be displayed. But I will show that later in the implementation of that. But as for the actual data that you see here, which you see the left joystick and you see the right joystick, if you move one of these guys, you get your readings, which this will be shot out to the Jetson Nano when we have Bluetooth capabilities ready. And this is also does the exact same thing the right analog stick does. And you got your file button, which as of right now there is no data to send, but we will as we get the PCB and hardware all populated. As you can see, we got the connect to Bluetooth devices, which as long as you're in Bluetooth pairing mode, you click get devices. It'll read back anything in your vicinity that has pairing on right now at this instance. So, come on, there you go. So S10 Plus, that's my phone. Connect to device. And as you can see, we are connected. Hopefully you can see that. So Black Dragon is my computer. We go ahead and exit out of here. Connect back in. You still see this is here. We're still connected. Hasn't left. And yes, now for actual streaming capabilities, we have our GStreamer pipeline, which is what we're using to connect through SSH just for now. Later on, we'll be having a script that once we turn the Nano on, this will just continue running for what we need to. And we shoot all of our stream towards a UDP source, which we pick up later onto the actual controller. And we use VLC to pick up that stream. So I'm going to go ahead, run my GStreamer pipeline. As you can see, it's creating it. We are good. And right now, this is the GStreamer pipeline for testing latency, which is what I've been using in the past week or so. So go ahead, close the application, reopen it. Now once we reopen it, it should just open up. And there we have it. There is our actual camera, which I will go ahead and show you guys. You guys can see here. You see our latency, which are damn near right on top of each other. Very slight latency. And this is what we'll be using to read in our object detection and everything from our tank in the future here. Very soon future. As you can see for the video to our right, this is the training that we have so far using SSD BobbleNet. This is the actual stream that will be displayed within our application on the stream that you saw previously.
Hi, my name is Skylar Burns, and I'm going to be doing the tank tread demo. We will start the demonstration by applying various voltages to the tank tread's servo motors. These motors typically operate at 7.2 volts. For this demonstration, we are going to show you the operation speed under 25%, 50%, 75%, and 100% load. These percentages will represent the duty cycles of the PWM control signals that we will be operating the motors with. The first voltage, which we will see in the video, is 1.8 volts. This correlates to 25% maximum operational speed of the motor. Here we can see that the motor is moving pretty slow, especially considering that it is free floating, therefore not under load. Here we will see the motor operating at 50% duty cycle. This is roughly equivalent to 3.6 volts. As you can see, the treads are moving much faster than the 25% duty cycle. Now we will set the motor to operate at 5.4 volts. This is 75% duty cycle of our total voltage. As we can see, the motor is moving much quicker than compared to before. Lastly, we're going to show the tank treads operating at 100% duty cycle. This means the servo motors are operating at 7.2 volts. This demonstration represents the fastest the tank will be able to move using the current voltage translation that we have applied to the circuit. Here we can see the overall design of the tank and our test setup. The tank treads have a built-in dampering system using a spring, so when it goes over an object, the tank treads are able to move up and down and work itself over the object. Lastly, we can see the underneath of the tank, which just consists of some wires. Here we can see a voltage reading of the 4 AAA batteries hooked up in series. Each battery has 1.5 volts, so when we connect 4 of them in series, we should get roughly 6 volts. In this demonstration, we will show the tank running at roughly 6.2 volts. This is roughly equivalent to 90% duty cycle of the total voltage that can be applied to the circuit. Lastly, we're going to demonstrate the off-road capabilities of the tank treads. Unfortunately, in our demonstration, my shoelaces got entangled in the tank tracks, causing the tank to stop.